that you guys just talked about when we graded the homework. So these right here, these are our go-to equations that allow us to go between the 4 variables that are the most important: pH, POH, H plus, and OH minus. Fair enough? And you guys did a worksheet that allowed you to go back and forth in this playground. But typically what happens is we don't have an H plus just walking around and all of a sudden it's like, doop, and jumps into a thing of water and we're like, oh, let me calculate the pH. That doesn't happen. What happens is this: we take acids and bases and we throw them into water, and then we determine what the pH is. Are you okay with this idea? Now, in fact, all reactions that we're going to deal with are going to involve us throwing stuff into water. So our mantra is going to be simply this: if I don't know what to do with something, if I give you something, an acid or a base, and you're like, what do I do with this? You throw it into water every single time. And we'll write equations that show what's happening when we throw things into water. Is that fair? So let me start off with the easiest way to determine pH, and that's with dealing with a strong acid or a strong base. Now, can you acknowledge that there's only 6 strong acids that we know of, right? CBS, PIN. Remember those from before? So what I could do, and I'm going to show you an example of this really quickly. If I said, what is the pH of 0.200 molar HCl? That would be a legitimate question, and this is how our pH questions will be directed in the future. We'll give you an acid, we'll give you a base, and we'll ask you to determine what the pH is. Now, what you should know about all strong acids is that when you throw them into water, so if I throw this into H2O, they 100% break apart into H3O plus and Cl minus. Another way of doing it is this, and I want you to see how this expression and this expression are exactly the same. Ready? If I write it like this, HCl, and I put the letters AQ next to it, what does AQ mean? Aqueous, which means that something is dissolved in water, right? So instead of saying HCl being thrown into water, I could say HCl aqueous, and when HCl gets thrown into water, it becomes H plus aqueous and Cl minus aqueous. Again, there should be aqueuses here as well. This is a liquid and this is aqueous. So these two expressions, they show how HCl 100%, actually I should not even, I'm not going to draw even a backwards arrow. They 100% go to H plus and Cl minus. So what I'm going to do is I'm going to introduce you guys to an ICE table, or an initial, change, and final table. But here's what I'd like you to start off with here. Initially, in this problem, don't I have 0.200 molar of the HCl? If you're having trouble, I would encourage you to read. So this is what we read, right? And it tells us in the problem we have 0.2. Too sarcastic? I feel like that might be a little bit too much for us here, last period of the day. We have 0.200 molar HCl. Now, initially, would you agree with me? I have none of this and I have none of this.
Wait, why do we have none of this?
Because I start off with only my acid, right? I throw it into water. And when I throw it into water, it 100% breaks apart. So what that means is that at the end, I'm going to write F for N, so I and F. I'm going to have 0 of this. And then I'm going to have 0.200 molar of this and 0.200 molar of this.
Whoa.
I want you to wrap your brains around that before I go any farther. Initial and final.
Wait. So we made double.
No, you broke it apart.
We made 100 or something? Oh, no, because it's the same.
Wait, but what if HCl produces 2 H's to each Cl?
It doesn't. But let's say we had this. So watch. Let's say this is my HCl, right? So follow this if you would. What if I told you I had one of these? You're okay with this, right? let's do this. So let's do it like this. We have one bled, black and red together, right? One bled. And if I were to break it apart, would any of you be like, okay, don't I have one black and one red when I break it apart? And none of you be like, whoa, 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 Mr. Teacher person. You can have one of this, but then also have one of each of these things. That's double the amount because we broke it apart. Are you with me? So if I told you, wait for it, I have 10 of these. And I broke them apart. Wouldn't that be 10 of these and 10 of these? Please say yes, because it's going to make me feel as a complete failure if I give you the most incredible, simple example ever and it's still not hit you. So follow this for a second. If I have HCl, for every one HCl I have, if I break it apart, wouldn't I have one of these and one of these? No matter what quantity of this I have. I happen to have 0.200 molar of this, right? So if I have 0.200 molar of this, when I break it apart, I should have 0.20 molar of this and 0.20 molar of that. Does that make sense to you? I do understand the confusion of going, well, wait a second, how do you have the same quantity of this as you do of these two things? But just think of it as splitting apart. None of us is going to have trouble with the idea that the amount that we have together is going to be the same amount as each of these individually have when I split them apart. Does that kind of make sense? Now, I want to point out something here to you because this is really, really important. We originally had a certain molarity or concentration of an acid, right? But when we throw it into water, at the end, don't we have a certain concentration of H plus and a certain concentration of Cl minus? Now, what does the question ask me to solve for? pH, right? In order to figure out pH, don't I need to just know what the H plus concentration is of something?
Which we know is 0.2.
So right now, we know it's 0.2 molar. So if I wanted to solve for the pH, isn't pH going to be equal to the negative log of my H plus concentration, which in this case happens to be pH of the negative log of 0.200 molar. Can someone punch that out in their calculator? And incidentally, you all need your calculators and you all need to be functioning with them right now. I want to appreciate this because normally when someone doesn't have something, they avoid eye contact, but that's a brash move to stare directly into my eyes when you don't have something. That is, God, you know what? I admire that. I admire that greatly. Anyone else actually have a calculator with them? They want to punch this in? And would you mind showing him how you punch in the stuff in the calculator? What's that?
I said, so hitting this.
I should not laugh at that, but it's kind of funny that he says that.
I've been using my computer for the whole.
Yeah, that's not going to work anymore with this stuff.
I actually.
So let's come back to this here. What number do you get?
0.69.
0.69 is my pH. And by the way, didn't we have 3 significant figures in our problem?
Wait, it's 7. Oh, it's 6, 9, 8.
698?
699. For the round up.
699? You guys are messing with me now, aren't you? So 699, and watch. See these 3 numbers here? The significant figures in a pH problem, because this is what my pH is equal to, right? My pH is equal to 0.699. The significant figures come after the decimal. So 0.699, because we had 3 significant figures in the original problem, that's how many we have in our answer. Now, do you realize they could have also asked me for the PCl, the negative log of the Cl? But we don't, because we don't care about the Cl minus because we're super ugly that way. Like literally, every single time I imagine when we're solving for this, we care about the H plus because the H plus is part of the whole dynamic of H plus and OH minus and the whole thing. We do not care about Cl minus. We really are elitist when it comes to this. Cl minus are like, well, what about me? Calculate me. And we're like, no, we don't care about you. But if we wanted to, wouldn't we also say that the PCl would be the same number, but it has no use to us? Oh, by the way, if I asked you in this problem, what is the pH of 0.200 molar HCl? Couldn't I also have asked you what is the POH of that?
Which would be like 14.
14 subtract this, right?
13.341.
Sure. Good. So you're proving you don't need a calculator.
Yeah.
Solidly done.
I can do logarithms.
Also, if they asked in the problem, what's the concentration of H plus, wouldn't that have been the easiest problem ever? Because whenever you have a strong acid, the concentration of the strong acid is the concentration of your H plus. also your Cl minus, but we don't care about the Cl minus. Would you agree with me on that? So there are 6 acids, if you ever see them. Hydrochloric, right? Hydrobromic, hydroiodic, sulfuric, perchloric, and nitric acid. Those are the 6 acids. The only 6 acids that when you throw them into water, they 100% dissociate. And here's what's really cool about this. You are going to love strong acid and strong base pH calculations, because whatever the concentration is of your strong acid, by default, you know automatically that's the concentration of your H+. Is that okay? Now, similarly, the same thing happens with our bases. So bases work a little bit differently, and I'm just going to show you this without doing a whole ice problem, because the reality is this. Did we need to do this whole table to just go, oh yeah, I have 0.2 molar of an acid, therefore I have 0.2 molar of H+. Wouldn't that now have been an easier way of doing it? Yes, teacher. You can't see the heads nodding here on the screen, but they're all in agreement. Yes, Hayden. I cringe.
Last problem, we had the H3O and the Cl, right?
Mm-hmm.
So it was the Cl just because it was the hydrochloric acid,
Mhm.
and because in our problem on the notes I have notes for the record,
Good job.
is H3O plus, which is
H+.
So is that always going to be there?
Yep.
And the
So if we
only-
throw something into water, the way we say H+ is we say it H3O+.
yeah,
It's the same exact thing.
I remember we said those are the same thing.
Yeah. So in the first example I wrote on the top of the board, it had H3O+ plus Cl minus, right? Which is the same thing. I wanted to make it easier for you to watch. And so I just said HCl breaks apart into H+ and Cl minus.
Okay.
Now,
So,
Now, can I make it really simple for you here?
yes, please.
Every time that we do a pH problem and we're dealing with a strong acid, we automatically know what the H+ concentration is, because it's going to be the same as whatever the concentration is of the strong acid. Are you all with me on that here? I'm curious. What were you staring at right there? What were you staring at right there?
I was listening, but I was like,
No, I was asking actually, Caroline.
oh.
What were you staring at right there? Oh, I didn't even lose to something like grandiose. It wasn't like some dancing monkey or something. That would be cool. I realize I'm being recorded right now. So yeah, last clear today. By the way, couldn't I have also asked, instead of what is the pH, couldn't I have said what is the OH minus concentration of this? Because if I know my H+, can I figure out my OH minus? And then couldn't I figure out the pH? So as long as we have this table over here, we can do any calculation that we want. Now, there are slightly more strong bases. So if I give you a strong base, for example, and I said this, what is the pH of 1.30 times, oh, actually let's do 1.30 molar NaOH. Now, I'm not going to set up an equation for this because I just want to do proof of concept here for you. This is a strong base, which means that it will 100% break apart. So NaOH will break apart into Na plus and OH minus. Agreed?
Yeah.
So whatever my concentration is of my base overall, won't that be the concentration of both my Na plus and my OH minus? But of these two, Na plus and OH minus, which one do we actually care about? Try again. We only care about OH minus, right? You really had a good shot at that doing it, but not quite. So instead of going through this entire equation, couldn't I just go, well, what that means is that really I have 1.30 molar OH minus. Isn't this what this means?
Oh, I see.
Yeah? So what does the OH minus allow us to then figure out? Yeah, we could do it one of two ways, couldn't we? Couldn't I take the negative log of my OH minus, right? If we look at our formulas on the side over here, couldn't I take my negative log of my OH minus, and wouldn't that give me my POH, and then subtract that from 14? That'd be one way. Or what you suggested is, couldn't we take my OH minus concentration and divide it into 1.0 times 10 negative 14? Wouldn't that give me my H plus? And then take the negative log of that to figure out my pH. Yes.
I'm sorry, I'm just trying to make sure I understand. So a strong acid or a strong base, the molarity equal to the concentration?
Absolutely.
Okay.
Did y'all hear that? Repeat it again, and that's worthy of an applause. Repeat it again loudly and clearly. Say it again.
So in a strong acid or a strong base, the molarity is equal to the concentration.
Correct. The molarity of either your H plus if it's a strong acid, or the molarity of your OH minus if it's a strong base, is equivalent to whatever they gave you as in the problem. So in this case right here, let's do this together. If I know that I have 1.30 molar OH minus concentration, which way do you want to do? Do you want to divide into 1.0 or do you want to take the negative log of it? Negative log. So let's go POH, and wouldn't that be equal to negative log of my OH minus concentration? And if I did that, what am I going to end up for my POH? Did you calculate it? Yes.
It's 0.13.
So you got 0. What is it?
113.
Negative point. What is it?
114.
0 or 0.114.
Well,
0.114. Now that's a weird number, isn't it, for the POH? Let's flip it into our overall equation. Doesn't it say pH plus POH equals what? 14?
So it's gonna be.
So if my POH is negative 0.114, mustn't my pH in this case be equal to 14.114?
Have negative pH.
Not negative pH, negative POH.
We can never.
You could, because here's the thing. We're dealing with exponents, right? So can't you have positive exponents and negative exponents? And the negative log is the opposite of your exponent. So if my exponent happens to be a big positive number, then you'd expect that your negative log would be a negative number. So this pH scale that we say is between 0 and 14 actually can go up to like higher than 14, and it can go lower than 0. Are you with me? So this is kind of a weird example where, and incidentally, if we're trying to determine, hey, I wonder if this solution is basic or acidic, isn't 7 neutral for pH? If my pH is 14.11, what may we safely say about the acidity or basicity of this solution?
It's very.
It is way, way base. You cannot get more base than over 14. Are you okay with that? This is because whenever we do our scale, remember that 7 is neutral. Under 7 is acidic. Above 7 is basic. Yes? Now, here's where we get on the fun ride. The problem we face is this. Not all of the acids and not all the bases we deal with are strong acids or strong bases. Before I even move on to this, do you have any questions on how we would solve a strong acid or strong base that go beyond what Caden so neatly synopsized, which was, if you're a strong acid, whatever the concentration of your strong acid is, that's your concentration of H+. If you're a strong base, whatever your concentration of your strong base is, that's the concentration of your OH-. And once you know you're either H+ or your OH-, aren't you going to go into the playground, which is these equations, to figure out whatever they're asking you to solve for? But that leaves us with the terrible, terrible realization that the majority of acids are not strong acids, and the majority of bases are not strong bases. So how do we figure out what the concentration is when not all of it separates out? And that's what we're going to figure out right now. We're going to start doing one at a time. We're going to start figuring out how to figure out the pH of a weak acid. So if you're doing your notes right now, do figuring out the pH of a weak acid. Go.
So if it's a strong acid or a strong base, it will have either hydrogen or the OH-.
Correct.
So that's just the one we care about.
That's it.
Okay. So
They'll have some spectator ion. Like, remember we talked about spectators before? Like in this case here, they had Na+. And Na+ is like, hey, what about me? And we're like, we don't care about you. Why? Because you're not OH-, you're not H+. I know it's cruel, right? Now we're going to get into the idea of what happens when we're dealing with a weak acid or a weak base. But let's specifically talk about weak with weak acids. So I'm going to take the example of acetic acid because we worked with it before. So here's acetic acid. Acetic acid, Ka equals 1.8 times 10 to the negative 5. Write that in. You're not gonna. It will not make sense right now, but it will in a minute. I'm gonna keep on trying blue pens until I get one that's new. Has an initial concentration of 1.30 molar. What is the pH? Actually, I'm going to ask this first. What is the H plus concentration? And then what is the pH? So I'm giving you something called acetic acid, and I'm asking you, what is its pH and what is its H plus? Yes.
What is the really long line that starts with the C at the end of it?
Concentration, initial concentration. So this, you may realize, is acetic acid, HC2H3O2. Agree?
Sure.
It's acetate with a hydrogen in front of it. Do you think I enjoyed writing that on the board?
No.
I did not. Why? Because I don't like writing a long, acidy sort of equation on the board. However, what we can do, and all we can, well, at least now I know there was someone out there. Right?
No, that was.
All right. So what we can do, and this is really important, we only really care about the H, don't we? Agree? Now, this could be anything because we don't really care about it. So what we can do with this, okay, who's distracting out there? Because that is, oh, he's trying to get into the other room. That's a drama. I get sucked in. So instead of calling it acetic acid and writing this whole thing out, we can make an abbreviation that abbreviates this. So I like abbreviating this with AC. So this here becomes AC. So acetic acid becomes an H with our ending, AC. Now, here's where every single time, whenever they give us an equation and it's not a strong acid, now we're going to know it's not a strong acid because they're going to give us a K value. Now, you remember from our equilibrium how K determines our products over reactants and the whole thing? Okay, so this is not a strong acid. So what we're going to do is we're going to throw it into water. So here's what we're going to do. We're going to take this HAC and we're going to throw it into H2O. Now, watch this if you would, and we're going to do a double arrow because if you're not a strong acid, you will come, an equilibrium will form. So if this is an acid, what does it want to do? But what does it want to? What do acids want to do with their hydrogen?
Get rid of it.
Get rid of their hydrogen, right? So won't this want to get rid of its hydrogen to whatever wants to pick it up? In this case, water is going to want to grab it. Are you okay with that? So if that happens, if this gives up its hydrogen, won't the water pick it up and want to form H3O plus? And what's going to be left over?
AC.
The AC. But it's going to be AC minus because it's a negative ion. So in essence, what this is, and I'll show you what actually is happening, and I'll show you how we break it apart. This is acetic acid. We throw it into water, right? And on the other side, we're going to form H3O plus, and what's left over is going to be C2H3O2 minus. Would you agree with me that this is preferable to write out than this? And you can do that every single time that you have a weak acid. You can, unless it's a really short, like HF. HF is a weak acid. So that'd be easy to break apart into H plus and F minus. Yeah? Now watch. I'm going to introduce you to your first ICE table. So this is ICE, I-C-E, and it stands for initial, change, and equilibrium. So lock in right now. Sometimes you'll and I'm going to write the letters I, C, E. Sometimes they call it Rice tables because the R stands for the reaction. So when you do a Rice table, you're going to write the reaction, and the reaction's always going to be you throwing in an acid into a water. Always. And what's going to happen? The water will always grab a hydrogen, and then whatever's left over will be your base, which we don't care very much about. Okay? Now, let's go back to the original problem. And what did they initially start us off with in this particular problem? Yes, correct. But what did they initially give us concentration-wise?
1.3.
Didn't they give us 1.30 of this initially? Are you okay with that? Oh, by the way, this is a liquid. This is aqueous. This is aqueous. And this is aqueous. So that means that our liquid we don't care about in terms of equilibrium. It never is involved in our equilibrium expressions. But if I start off with 1.30 molar of this, I have none of my H plus and my Ac minus. And notice how I shifted between calling this hydronium and H plus. It's the same thing. Anyone have trouble understanding that initially, before we throw it into waters, this is our initial part, before we throw it into the water, we have only the acetic acid and we have none of our H plus or our Ac minus. That makes sense. Now, here's the difference between weak acid problems and strong acid problems. Please focus in, because like literally the next like 10 minutes will make this entire section incredibly easy, or you're gonna spin. I'm hoping it's incredibly easy. Does all of this acetic acid 100% break apart into H plus and Ac minus? No. What are the only acids that do that? Strong acids are the only ones that 100% break apart. So what we know is, of this 1.30 molar, a portion of it is going to become H plus and Ac minus, but a lot of it's going to stay as this. So here's where algebra is going to come into our rescue. So here's what we're going to do. We're going to say, and see if this makes sense to you. Won't a portion of this leave? And whatever that portion is, since this is a 1-to-1-to-1 ratio, just like when we separated our pens, whatever leaves here, won't it form here and here? So what we're gonna do is we're gonna say, hey, whatever leaves, we're gonna call it X. So the change for my reactant side is we're gonna lose X amount of our 1.30 molar. We don't know what that number is yet. But we know that whatever we lose here, since it's a 1-to-1-to-1 ratio, we're gonna gain here. So we're gonna gain X here, and we're gonna gain X here. Anyone having trouble with that idea? Now, because we're good with math, we're going to add these two together, because at equilibrium, when everything gets evened out, the amount of acetic acid we have is going to be lessened by whatever left it. So at equilibrium, couldn't we say that we have 1.30 minus whatever left? That X is how much left. Yeah. Now, didn't we start with 0 H plus or H3O plus to begin with? And didn't it gain X? So at equilibrium, wouldn't this be X? 0 plus X is X. And similarly for this, 0 plus X would be X. True story?
Yes.
So we know what the equilibrium values are. 1.30 minus X, X, and X. Super. And would you agree with me that if we know what X is, won't we know what H plus is? And if you know what H plus is, can't we figure out pH? So that leads us to our equilibrium expressions. So you guys remember how we did equilibrium expressions the other day? What I want you to do is for this reaction right here, I want you to write the equilibrium expression on the sides. We're going to do it over here. I want you to write what the K expression would be for this reaction right here. Any guys need a booster to how we start with this?
Oh, reactants.
Okay, isn't it products raised to their coefficients over reactants raised to their coefficients, excluding liquids and solids? So can you write the expression for this right here, for this equation right here, write the expression which is products raised to their coefficient over reactants raised to their coefficient, please.
Including H2O or not?
Is that an aqueous or a gas?
No.
Then we don't want it. Write it, give me a wave as soon as you've written it. Okay, I'm going to jump forward here. So I'm going to call this K, and because I like to let people know what type of reaction I'm dealing with, I'm going to write the subscript for whatever this is. Isn't this an acid? So I'm going to call it Ka. We're super creative that way. And that's going to be equal to my products raised to their coefficient. So if I look over here at my products, don't I have H3O plus with a 1 in front of it? And don't I have Ac minus with the 1 in front of it? So over here, I'm going to go like this. I'm going to write on the top, H3O plus raised to the 1, but that's a nothing burger, right? And then I'm going to put Ac minus also raised to the 1. And what do I have on the bottom? Isn't this my product? Isn't this my reactant? And isn't there a 1 in front of it? So wouldn't that be HAC raised to the 1? Now, remember at the very beginning of the problem, I gave you the Ka? That's because in order to solve for a problem like this, you need to know what the Ka is. So really quickly, aren't there 4 variables right here? So we're going to plug in all the information for equilibrium into this equation that we now have. Yes? So let's do that. First of all, don't I know what my Ka value is from the problem? Isn't it 1.8 times 10 to the negative 5? So I'm going to put that over here as 1.8 times 10 to the negative 5. Then I'm going to put my values on the top. So it's going to be x times x, because those are my 2 equilibrium values for H3O plus and AC minus. And on the bottom, I'm going to put 1.30 minus x. Welcome to algebra. Now, are any of you guys familiar with the quadratic formula?
No.
Or, oh, you guys have the song, the same. That's very cute. Or are you familiar with how you solve for polynomials? Now, I will say this, and this is kind of funny in a not funny way at all, but you guys now with your calculators can actually punch this in without having to do any brain power at all, and it will spit you back what the x value is. Are you aware that your calculators have this ability to do it?
I've been trying to figure out how to
Yeah, it involves having a calculator first, so that's probably your first strike.
That's where I was going.
Now we can get back on the right path. But let me show you something that's actually going to make your math a little bit easier. Would you agree that if this x wasn't here, would this become a much, much easier problem?
Yes.
Okay, so let me show you a neat trick. And this only works with weak acids. Listen carefully on this. And it only works when you have a very small k. Now, 1.8 times 10 to the negative 5, would you agree with me that times 10 to the negative 5 of your products versus your reactants is a pretty small number? That means you have essentially 10,000 times more reactant than you do product. And aren't our products our x values here? Now, watch. What that means is this. If my k is very small, it means that we have very little product or very little amount leaves the original amount. So what we can actually say is this. If this amount, x, that leaves the original amount is less than 5% of the original, we can consider it to be negligible. It doesn't matter to us. So we are able to do this, and this is super fun. Whenever we have the initial amount, if you guys realize that this value right here is our reactant initial amount, and we lose some value from it, if our k value is really tiny, which it is, the amount that we lose from the 1.3 is so small that we can do this, and we can write a line through it, and we can call it the 5% rule. And 5% rule simply says that if our x is less than 5% of the original amount that we have, we can ignore it in our math. Stay with me. Stay with me. Now, the first time they showed me this, I was like, wee, let's get rid of the x's. So I'm like, this x gets canceled. And then I'm like, this x gets canceled, and this x gets canceled. And then I had 2 numbers that were not the same equal to each other. And the question is, why can't I get rid of these x's here? Well, let me show you something that's actually kind of important. How much did we have originally of my H plus? I'm pointing right at it in case you're having trouble.
This is 0.
We had 0, right? If I gain x and I had nothing to begin with, can I say that x is negligible to me when I had nothing to begin with? It's kind of this principle. Let's say I am a billionaire, a multi-billionaire. We can only dream, right? That's like having 1.30 molar. And if that billionaire loses $1 or $5, do you think he's going to be like, oh no, what has happened to my fortune? He's not going to care because this value compared to what he had originally is so small. Do you follow this here? But what if I'm a zero-aire? What if I have no money? So if I'm one of these two that starts off with nothing and you offer me X, you offer me a $5 bill, will that be nothing to me if I had nothing to begin with? No, I'm going to consider that to be significant. So I cannot get rid of these two x's because they are not nothing compared to what I started with. Does that make sense? Yes.
So you cancel out the x because it is less than 5%.
It's less than 5% of this original amount right here.
How do we know what X is?
We're going to solve for it right now.
Well, right, but how do we know it's less than 5% if we don't know?
Great point. Great point. And here's the assumption that we're going to make, and we're going to test the assumption afterwards. The assumption we make is this. If this K value is times 10 to the negative fourth or smaller, that means that the products compared to the reactants are insanely small. Which means this. Aren't my products, isn't it X and X on the product side? So if I'm losing X from my original amount, and X has to be really small because my K is really small, I can assume it to be negligible. Now, Kaden, we're going to, at the end of this problem, we're going to go back and we're going to prove that it was less than 5%. And if it's not less than 5%, then we're back to having to deal with a quadratic formula and a polynomial, which is not very fun. Now, those of you who are like, my calculator does everything for me, then you can literally punch in these three things, including the X down below, and it'll spit back an X value for you. And that X value will be equal to both your H plus concentration and your AC minus concentration. We don't care about AC minus, we only care about the H plus. Yes.
How do we write, like how would we type that into our calculator?
Your calculator has a function where you can actually talk to your math teacher.
It's solve parentheses the equation and then comma.
I do not know how it works on your calculator, so I can't help you with that. But I do know that my AP kids, they now scoff at these problems because they don't even bother doing any mathematics on it. They just plug the numbers into their calculator. They've become really proficient with it.
Can we just do that?
You can. Absolutely you can.
Okay.
But let's pretend that this becomes an easy problem for us. And let's pretend that this is gone. And by the way, we call this dead frogging. My students gave that the name because it doesn't look like kind of like a dead frog and the tongue sticking out. If you ever hear that, I'm sorry. No frogs were harmed in the making of this problem, in case you're wondering. Now, if I want to isolate my x, and this is gone, wouldn't that be equal to this? X squared on the top, right? And wouldn't I wouldn't I multiply my 1.8 times 10 to the negative 5 by 1.30? If I wanted to get it off the bottom. Is everyone okay with that? And if x squared is equal to this, couldn't I go x is equal to the square root of 1.30 times 1.8 times 10 to the negative 5? Can someone do this for me on their calculator, please? And by someone, I mean, can all of you do this on your calculator, please? Except for Hayden, who will imaginarily punch numbers in the air on his imaginary calculator. Okay, anyone have a number for our x? It's going to be a small number. Jane, you look like you punched in. Can you help me, please?
0.004837.
Say again, 0.000, only 2 zeros or more?
Only
2 zeros, and then what?
4837.
48, let's call it 484. So that means my x is equal to this right here. Agree?
That's small.
It's a really small number, especially when we compare this to 1.3. By the way, could we have written this as 4.84 times 10 to the negative 3? Would that have worked as well? And sometimes our calculators will spit out the E key on there, and that works as well for us. So watch. What is x actually equal to at equilibrium? Let's backtrack to our original problem. What is x equal to? Isn't x equal to my H plus concentration?
Yeah.
I mean, x is equal to my H plus concentration, and it's equal to my acetate concentration. But in my problem, didn't they ask what is the H plus concentration? So couldn't I just go like this? This is equal to this, which is equal to my H plus concentration. Why do we love that we have our H plus concentration right now? Because once you have the H plus concentration, can't we take the negative log to get to pH? Since Jane's been doing all the hard work, who else has a calculator? Can you guys, and by the way, I don't want to threaten, so I'm going to idly threaten anyway. Bring your calculator next class, or else. There really is no, here's the unfortunate thing. I don't know how I'm going to punish but you know me, I'll figure out a way. That is, if you were a teacher, that would be a horrifying way you could punish your kids, yes.
So I typed it in and I got two different numbers.
For-
none of which are that number,
Uh-huh,
but they're very close.
and what's the other one?
It's 0.004846.
And,
That one's negative, that one's negative.
okay, there it is. You can't have a negative concentration.
Okay.
So that, if you punch it in for polynomials, and by the way, when you guys do quadratic formula, you guys remember when you did it? Didn't you get a positive and a negative value for your x? That happens for all polynomials.
I got 43 though.
Okay, well then, that's because we are making some assumptions here. So if we go 484, do you realize that the difference between what you just typed in, Caden, and this is 1, 2, 3, 4? It's in the 100,000th spot. It's not really going to change our number, right? Can someone here take the negative log? So wouldn't our pH be equal to what? 2.315. And I'm delighted you kept the 3 significant figures in here. 2.315 is our pH. And does that make sense to us? Well, yeah, because aren't we dealing with an acid? And shouldn't our pH be below 7? Yeah?
It's 2.5.
2.315. So if you take the negative log of the H plus, you're going to get 2.315.
So what, if it's a weak acid, would it be closer to 7?
Oh, that's interesting. So weak acids and strong acids, that just determines how much H plus you have. So let me back it up. pH just determines how much H plus you have. So follow this. Would it make sense if I had a large amount of a weak acid, it could produce just as much H plus as a very small amount of a strong acid? And so that's really what's happening here. So it's a weak acid, but it doesn't, because I have a lot of it, I can still have a pH that's pretty low. Now, remember I said that there's a 5% rule here? And what I said therefore is this. This X needs to be less than 5% of this. Now, how do you determine what the percentage is of something else? Don't you put it over the thing? So couldn't I do this? This is for percent. And we call this percent dissociation. So percent dis equals, and we're going to take our X value, which is 0.00484, and we're going to divide it by our original value, which is 1.30, and then we're going to times it by 100. So can someone put the numbers in there? 0.00484 divided by 1.30, and tell me what the number is. Feels like you could just be able to just punch these two numbers into your calculator. Take this and divide it by this. Yes.
Can I do 0.00 divided by 0.05 and see if the number is bigger than the
That's another way of doing it, but let's do it this way because I want to do proof of concept, right? 0.00484, 0.003, that's after you multiply by 100 or not?
That's not.
So if I have 0.003 and I multiply by 100, won't that be 0.3%? I'm going to guess that 0.3% is less than 5%. So were we okay with making the assumption that this X value is very small compared to this? Yeah, because the X value is only 0.3% of this original one. That makes sense? What I just showed you here is something called percent dissociation or percent ionization. Now, this has been a lot to put into one lecture. So we're going to revisit this. I'm not going to give you problems on this yet until we have some time to do some more practice together in class. That includes people that are online. However, I'm going to give you an incredibly brief homework, and it is on Cengage. I know it's been a long time since we did this. It literally is one problem, and it asks you to do some pH calculations with strong acids. So literally, it's online. You guys know your Cengage account from before? It's one problem. It has 3 parts to it, but it's one problem. That's what your homework is going to be. I'll put it on the portal as well. What's that? Yes, you do. So it's going to, literally, the problem is like, it's worth 1 point, I think. So you'll get a certain number of points out of 1. Anyway, that's the lecture for today.